hi everyone, welcome back to another video. Today I'm trying a different camera angle. I know it's a little slanted, so bear with me on that. But today we're going to be talking about position, velocity, and acceleration time graphs in relation to the MCAT. So if you are a first year physics student, this is not getting into calculus. This is going to be pretty basic. We're just talking about simple stuff. And the reason I'm making this video is because for me, this is a topic I feel is free marks, and this is something that you should be able to get down and be able to get it right whenever it comes up on an exam. So let's get into it right away. Let's not waste any time. So there's some important stuff you need to know. I apologize for the glare on the screen here. Right here, we've got a position time graph, okay? Now this is the most basic one you're gonna get. We've got displacement here on the y-axis, and ironically it's represented by x a lot of the time. You'll see that in the formulas. And we've got time here on the x-axis, right? And so what you want to know with this one is obviously you want to take into account whether it's displacement or it's distance, right? Because if it's displacement, we're talking about a vector quantity, right? And you know what that means from physics, but I'll reiterate it, right? It has a direction with it. It's not just a value like a scalar is, right? If I walk 2 meters this way, my displacement is 2 meters, my distance is also 2 meters. But then if I walk back 2 meters, my displacement is 0, but my distance is 4 meters, right? Because I've traveled 4 meters. But from my original position, I haven't moved, ergo my displacement is 0 meters, which I'm sure you already knew, but I thought I'd reiterate it. So when we're looking at a position time graph, we need to keep that in mind, right? So say this line right here, right? It's linearly increasing, right? And say it goes up to, I don't know, let's say this is up to 8 meters right here. Well, at time, whatever, let's say it's 4 seconds, right? How do we figure that out? It's pretty obvious, right? It's 8 meters, right? Because we end right up here, it's 8 meters. This is the simple one, right? But what information can we glean from a displacement time graph? Well, what we can actually figure out is the velocity, right? And this is where remembering how algebra works is really important. You remember the classic equation y equals mx plus b, right? Well, what does all that mean? Y-axis, right? It's a value at a specific point on the y-axis. So in our case, 8 meters. M, what is M? M is the slope, right? So we actually don't know that right now. X is going to be time, right? So it's 4 seconds here. So, well, we want to know what is the velocity here. What is M? M equals delta y over delta x, right? The change in y over the change in x, right? So what we're doing here, all we have to do is we have to do 8 meters, right, over 4 seconds. 2 meters per second. It's that easy. So when it's linear like that, it's really easy to figure out. Let's take a look at another one, right? What if it increases and then stops, right? And it asks you what the velocity is. Really, it's about knowing where the x is, right? Finding 4, and then going down and finding whatever this is 2. You know, you might have to do some approximation on the MCAT, but that's a fairly easy one, right? Okay, so let's move on to a velocity time graph. So velocity on the y-axis obviously is dependent. It is a dependent variable. It's dependent on time. Time is the independent variable. It's on the x-axis here. Okay, so if we get a graph like this, what can we figure out from the slope? Well, think about this, right? If you multiply meters per second by second, what are you getting? You're getting meters per second squared, okay? So you can figure out the velocity, the acceleration here by multiplying the velocity by the time, right? So let's take a look at this here. Or sorry, not multiplying it, dividing it, my apologies. So what we're doing again is a variation of this y equals mx plus b. We are doing m, the slope, equals delta y over delta x. And what is delta y in this case? Delta y is the change in velocity, right? So we're going from, I don't know, what is this here? Let's say, again, 8 meters per second squared, and it ends at 4 seconds. So we're doing, well, it's obviously, since we're starting at 0, right? And bear in mind that that is a change. It's not just the value of y at that point. It's the change in y. So if we started at 2 meters per second, it would be 8 minus 2 over, 4 minus 0, because we're starting at time 0. So let's just write this out here for a second. And then remember how things cancel, or in this case, don't cancel. Sorry. We're going to come out here with 2 meters per second. I don't know why I have a 2 there. My God. 2 meters per second squared. So that's what's important here. Slope on the displacement graph, that's going to give you velocity, right? Slope on the velocity time graph, that's going to give you acceleration, right? But let's ask ourselves a question. If the slope gives us acceleration, what does the area give us? And take a guess right now. Pause the video, take a guess. I'm sure you got it. The area is going to give us our displacement, right? Area is just delta x times delta y, okay? And let's just write this out for fun. So again, we'll say we've changed. We've gone from 0, my God, another 2 there. We've gone from 8 meters per second let me start over. Let's say we've gone from 0 meters per second to 8 meters per second in the span of this graph right here. And that span is 4 seconds. We multiply, right? And you can see this in the math. Like, you can see here that the seconds are going to cancel, right? Instead of divided, where these seconds are going to double up, they're going to cancel. And we're just left with this here. 8 times 4, we're left with 32 meters, right? It's that easy to get that from this graph here. Very straightforward. Let's look at acceleration. So really all you need to know with this one, the slope of the graph here is going to give us a value that is irrelevant to the MCAT. So you don't need to know it. Or really life science physics courses, you don't need to know it. So let's just talk about the area. So again, area, delta x times delta y. Let's switch it up. Let's say this is 10 meters per second squared. This right here is, I don't know, 2.5 seconds. I'm just making stuff up. Okay, so this is going to equal 10 meters per second squared, and I'll get out of the way in just a second, times 2.5 seconds. And so you can glean from that. It's almost as if when we're getting the slope, we're going up. You know what I mean? When I view them in tiers, I view it as displacement, velocity, acceleration. If we're getting the slope of a distance graph or a displacement graph, we are going to get the velocity. If we're getting the slope of a velocity graph, we're going to get the acceleration. And then the area is back down the other way, right? You can see right here, when we're doing the area, 10 meters per second squared times 2.5 seconds, right? And this is what I mean by the area, by the way, in case you didn't know, it's the area under the graph. So like integrals, if you've ever taken calculus, right? Cancel out the seconds. All of a sudden, shoot, my math, didn't even think to do the math, 4 meters per second. And we've got the velocity, right? We've gone backwards. But here's an important thing to know. Let's do another graph here. So, what does a graph like this tell us? This is a tricky one, right? All this says is that over this time period that this line goes, we're moving at a constant velocity. So what does that mean for our distance? It means our distance graph, if they give you a graph like this, and then they ask you to draw the distance graph based on that, it's going to look like this, right? Because it's a linear increase. Because we're moving at a constant velocity, we get a linear increase in our displacement, right? Because I'm always moving at the same speed, so I'm always increasing my displacement at the same rate, okay? Like, we can do another graph. We can do another one. So, and I'm sure you can guess this one. I probably don't even need to draw it out. If your acceleration is linear, what does everything else look like? Well, it's sort of the same thing, right? If we're linearly increasing acceleration, right, no, sorry, if our acceleration is constant, our velocity linearly increases. So our velocity is going to look something like this, right? Well, then the question is, what does distance look like? Well, distance is actually going to be exponential, right? Because our velocity is continually increasing, which means with each passing moment, we're getting faster and faster and faster. And so we're covering more and more displacement with each passing moment, right? So, okay, let's think of another one here. And you need to go back and forth with those, right? They might give you displacement and ask you to figure out what the acceleration graph looks like. And it'll definitely get more complicated. There'll be ones where at some points it's going constant, at some points it's increasing, at some points it's decreasing, right? So let's think of another one right here. Goes down to 0, right? So what does that look like? If this is linear here, right? This is going to be something like this. So, and ignore the values on here. We're just talking about the signs right now. Something like this. We are seeing an exponential decrease, right? So it's pretty straightforward. If something is constant, right? If it's constant, even if it's constantly negative, be aware that acceleration velocity can be negative. It all depends which direction you denote as positive or negative, right? So if it's negative, just be conscious of that and realize that that just means we're moving and we're starting to move in the other direction, the direction we've denoted as negative, right? So if, I don't know, you start out with something that's, and let's just erase this down here. I'm going to continue the graph down here, right? If we have an acceleration that is negative, let's say whoops, that's not a constant line. Constantly negative, something like that, right? It's negative, okay, that's fine. Negative 4 meters per second squared. And they can explicitly tell you that you start out at, like, say, 8 meters per second velocity, and they want you to do a velocity graph. Well, all you need to know is that you're going to linearly go down like that, right? And what that means is, well, we have a certain speed when we start, 8 meters per second in this direction, right? But we have a negative 4 meters per second constant acceleration. Some people might call it a deceleration, but that would just get confusing. If you're moving 8 meters per second in the positive direction and you have a constant negative 4 meter per second squared acceleration, that means you're slowing down, and as you get to 0, you're starting to move backwards and you're getting faster in that direction and faster in that direction. And that's how to think of like a negative acceleration, right? It's sure, it's slowing you down in one direction, but as soon as you get to 0, it's going to speed you up in the other direction, right? So yeah, and then with a displacement graph, there can also be a negative axis to that. So be aware of that, right? I think that's everything. If you have any questions, please let me know. Comment them down below. I'll try to get them answered. But yeah, I hope this was helpful to someone.